let's start. Yeah.
Sure. Hi, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce our prestigious speaker, Professor Dimitris Bertsimas. Professor Bertsimas is currently the Boeing Professor of Operations Research, the Associate Dean of Business Analytics at the Sloan School of Management at MIT. He has made great contributions to optimization, machine learning, and applied probability, as well as their applications in healthcare, finance, OM, and transportation. He has co-authored more than 200 papers and 5 graduate-level textbooks. He is the editor-in-chief of Inform's Journal of Optimization and former department editor in Optimization for Management Science and in Financial Engineering in Operations Research. He has supervised over 70 students who have become research leaders in their own fields. He is a member of the National Academy of Engineering and Inform's Fellow, and has received numerous research and teaching awards, including the John Neumann Theory Prize and the President's Award of Informs. And Professor Bertsimas is going to talk about machine learning and the modern optimization lens. Let's welcome Professor Bertsimas.
Hi, everybody. It was nice to thank you for the invitation. So my plan today is to talk to you about a collection of problems where mathematical optimization, particularly discrete optimization and convex optimization, can make a material difference in solving these problems, and in particular, improving the out-of-sample performance in statistical computation. So I'll be talking about sparse regression, matrix completion, and stable regression. And this is work that is based on some recently published papers. The paper on sparsity is joint work with Bart van Parijs, appeared in Annals of Statistics this year, 2020, but a few months ago. And stable regression, that paper with a current student of mine, Ivan Paskov, who appeared in JMLR just in December. And then another topic of interpretable matrix completion with another student, Michael Lee, who is under review at the moment, but he has not been published. So just for motivation, and by the way, please feel free to ask me questions and you can interrupt me. I recognize the audience cannot interrupt me, but the organizers can. So please, tell me if there are questions. I would enjoy interaction. So the motivation for this talk is the following observations: that continuous optimization have historically played a significant role in machine learning and statistics. And in the last 2 decades, convex optimization have had increasing importance. Areas like compressed sensing, matrix completion, among others, have benefited from the use of convex optimization. However, many problems in machine learning and statistics can naturally be expressed as mixed integer optimization problems. However, the general belief in statistics is that mixed integer optimization is really not a practical way of solving the problems, and the corresponding statistical problems are intractable, and therefore heuristic methods have been used. Lasso, for example, for best subset regression, or CART for optimal classification. However, in the last 30 years or so, if you look at the progress of commercial solvers, I'm looking at Gurobi, who's the predecessor of CPLEX. If you look at the total speed up, both from software and hardware, so the speed up is of the order of in the trillions times, 2.2 trillions. So I just repeated that something that in a mixed integer optimization problem would have taken 71,000 years to solve roughly 25 years ago can now be solved in a modern computer with today's software in less than 1 second. That's obviously a spectacular improvement in our overall capabilities. So reasonable questions, therefore, is given the dramatically increased power of optimization, mixed integer in particular, can we solve key machine learning statistics problems considered intractable a decade ago. And also, how do mixed integer solutions compete with state-of-the-art solutions in the field that are more heuristic in nature? That's one part of the motivation. The second motivation of the talk, later in the talk, is the following observation: randomization is a method of choice in a variety of problems in machine learning and statistics. In fact, the fields of statistics and probability are linked substantially. So there are classes that have titles, probability and statistics. Just to give you just examples of methods where randomization plays a critical role: bootstrap, selecting training and validation sets, randomized clinical trials, random forest, and so forth, use randomization in a very important way. So the question is, can optimization play a role instead of randomization? And finally, given, I will show you some developments, what are the implications on teaching for machine learning and statistics? I have been researching these questions for the last decade, and in 2019, last year, 2 years ago, I've published a book together with a former student, Jack Dunn, Machine Learning Under a Modern Optimization Lens, that in a sense summarizes the developments from my research in the last decade, including what I'm talking about today. So let us start with sparse regression. The sparse regression problem is the following one. So you are given data, y and x. So the yi and xi, but if you put the xi's as raw vectors, x is now the matrices of all the observations, is a n by p matrix, and the number of observations, p is the number of independent variables. So we are looking to find the beta. That's a regular regression with quadratic laws. Then I have quadratic regularization. And then I have the fact that we want the sparse regression, namely the number of non-zero components of beta should be less than k. So the way I start formulating the problem is the following. I write beta I. Whenever I have beta I have beta I times si, where si is binary variable, 0 or 1, such that the sum of the si's is less than k. That's what this models the problem as indicated. So the following problem can be written the following way. I minimize over the discrete elements, the s is 0 or 1, summing to less than k, and then the minimum over the continuous variables beta. But whenever I see beta now, I have S beta. S is a diagonal matrix of the si's. And then whenever I have beta I have Si beta I and all of its squared. Of course, Si squared equals Si because Si is binary. So I therefore minimize first over the discrete components, second over the continuous components of this function, which as a function of beta given S is a quadratic function. Quadratic functions, as we know from high school, or maybe first year calculus, can be solved in closed form. So if you solve this quadratic given over beta, which is a quadratic function S given, you have this function, namely that you minimize C of S, which is 1/2 Y transpose, an identity matrix in n dimensions, plus gamma. Gamma is the coefficient of the regularizer, plus the sum of Sj, Kj. Kj is the rank 1 matrix, Xj, Xj transpose. Xj is a column of the matrix X, inverse times Y, sum, and S is discrete. So this is an exact reformulation of the problem, except that now I have this is a convex function because Kj is a semi-definite matrix, rank 1 semi-definite matrix, but semi-definite nevertheless. So this function is convex. So we are minimizing a convex function in S, but binary. I pause here for questions, if any.
I think it's very clear, so we can move on. Yeah.
So somebody asked me, does the order of optimization matter on slide 8? And the order of optimization, I choose the order. It does not matter. Oops, that's a second now because I don't know how to get out of the, all right. It's clear then, I should continue. Yes? I need the organizer's help. All right, it's clear. But what we have accomplished here, and this is unlike something I have done in the past, I've written another paper also in Annals of Statistics with Rahul Mazumdar, in which we use big M formulations, the classical way. So this is, in a sense, goes against what we teach in classes. Namely, I formulated the problem in a nonlinear way, and this is the outcome. So now I want to minimize a convex function subject to binary variables. So now what I do is that, so I have a convex function C of S. So C of S is greater than the linearized version. So I have S bar. I can find a function that the first order approximation leaves the function to the right. So therefore, I can, instead of minimizing C of S, I minimize a C of S, the linearized approximation. I find another function, I approximate it and so forth. And then in the end, I find the solution. This method is convergent, but I have to solve linear optimization problems over binary variables, a problem that Gurobi or commercial solvers can solve fast. So that's the overall algorithm, that it's a cutting plane method. You start with S1, you optimize, you minimize S over, let's say, minimize Z, such that S bar plus the gradient S minus S bar greater than Z. You start adding the cutting planes, and then you finish. So that's a cutting plane method, provably convergent from earlier theory in the 80s. And what is exciting about, so we have a method that converges to provable optimality. And I would like to show you the level of practicality. So this is the time that lasso takes for P is the number of factors, N is the number of data. This covers both the high dimensional case and the regular case. And you observe that in both environments, the exact solution versus the lasso solution, this is a solution in seconds, is of the same order of magnitude. In fact, if anything, the exact solution is faster. The fact that it's faster is not so important. The fact that it's of the same order of magnitude is important. So in other words, the argument that heuristics are needed because the exact problem is not tractable, it doesn't, in my opinion, hold anymore. This suggests that we can solve large-scale problems, let's say, and the reason you have NA here is because of memory, not because of speed. So if you were able to have larger computers with more RAM, we'd be able to solve. In fact, in recent recent months, we have been able, because we had an application that was interesting to solve. What is more important is how is what I call phase transitions and the accuracy. So now we do experiments in which we generate data, which is X times the true, we have a particular vector, we generate data X beta plus E is a zero mean with noise, and we start increasing noise. So, and the way we estimate how good we are, we have two measures, the accuracy and the false alarm rate. So the accuracy is defined as the true support versus so let's say the true support is 1, 2, 3, 4, 5, okay? And beta star, what we find is 2, 3, 4, 5, and 6. In other words, it finds 4 correctly and 1 wrongly. So this would then be 80% accuracy, 4 out of 5, okay? Of course, the objective is to have 100% accuracy. And what is
Bertsimas, so one audience asks if you can explain a bit more on cutting plan. So I think it's from Isma Lenhardry. So the previous slide had a lot of content, and it would be great to explain a bit more.
So the cutting planes is actually a very simple method. So think of it as follows. Maximize, what we want is to minimize C of S, right? That's what we want. That's the exact formulation. So let's write it as follows: minimize Z subject to C of S less than Z, right? That's exactly the same problem. Now C of S is greater than equal than C if you have a starting point S bar. So you have C of S is greater than this quantity. So if I write it minimize Z subject to Z greater than this, that's a linear constraint in S because S bar is given. S binary. I solve this. I find this, let's say, a new S, call it S1. So I add another constraint that Z is greater than C of S1 plus the gradient C of S1, S minus S1. This is the second constraint. In other words, what I do, I find successive optima and I approximate the function by its piecewise linear lower approximation. In every time, I optimize a linear optimization problem, an integer optimization, binary optimization problem with only one continuous variable, Z. All the other variables are discrete. I do it successively, and what this suggests very fastly, you can find the solution.
Great.
Okay. So, so back to the definitions. So let's say beta true is 1, 2, 3, 4, 5. Beta star, let's say, is 2, 3, 4, 5, and 6. So in this case, the accuracy, you find 4 out of 5, 80%. But you also have found there's a false alarm because now you have one of the things you added, namely 6, is included. So the false alarm here is 20%, 1 out of 5. Right? So ideally, so what is perfect support recovery? When beta star tells you the whole truth, alpha A is 100%, and nothing but the truth, F is 0. Okay, so that's A, that's F. And this is the comparison between Lasso and our method. So this is the time. So this is N, the number of observations. This is the accuracy. This is the false alarm rate. And this is N. So notice what is happening. When N is small, you don't have a lot of signal. The time it takes to solve the red is our method is high, right? After a certain point, and definitely all the data I saw you is above that level, the time is actually extremely fast, faster than Lasso. Lasso is the blue. So Lasso is always fast. This method is fast when you have enough signal. Look at accuracy. The accuracy is at the same level of phase transition. The red is higher. So we have 90, 100%. And then after this phase transition, it becomes 100%. Lasso eventually gets to 100%, but at a later time. It has a phase transition, but later. But look at what happens at the false alarm rate. That the blue never goes to 0. So even for large data sets, n goes to infinity, Lasso keeps having false alarm issues. In other words, it finds the truth, but it finds also many other things that are not appropriate. Whereas this method, as n increases, for the same level of phase transition, becomes 0 in terms of false detection, false alarm detection. So in other words, it is known in the literature that false alarms are present in Lasso detection. In other words, it finds the truth, but it finds also other things that are not part of the truth. This method finds the truth and only the truth. And it has a phase transition. And there has been also recent work by one of my colleagues and a student of his, David Gamarin and Lias Davik, that proved this picture. So we have discovered this experimentally because we have the ability to do it, but they have proven mathematical theorems that are consistent with the picture I give you. So some final remarks on the topic is that traditional complexity theory suggests that the difficulty of a problem increases with dimension. This is what it means, that the problem is complex. However, this is not what we are seeing. Sparse regression has the property that for small number of samples, not large number of samples, this approach might take much larger amount of time to solve. But as the number of observations increases, it's much easier. So the opposite of what traditional complexity theory says. However, if you don't have enough data, the optimal solution does not recover the true signal because you don't have enough data to recover that. But as I mentioned, for large number of samples, this approach solves the problem very fast and recovers all of the support of the true regressor. So in recent times, we have generalized this approach and succeeded in many other sparse problems like logistic regression, time varying regressions and so forth. But I think the idea of using convex and discrete optimization method using cutting planes has been a success in this environment. I pause for questions.
So there was a question by Robert, actually. He was asking, what was the data generating method here?
I explained it. Here it is. Beta true is a particular vector, sparse. E is a zero mean noise, uncorrelated with the signal. In the paper, the one I told you with Bart van Parijs that appeared in Annals of Statistics 2020, there are correlated data, strongly correlated and so forth. The same phenomenon occurs.
So there's another question about, is large here means large N with respect to P or to the signal to noise ratio or something else? So
the experiments have N increases for fixed P. I forget what P was in this experiment. But as you can tell here, N and P can also be in the hundreds of thousands. So this covers, let's say for the case P equals 50,000, N equals 100,000. This is the case of regular regression. P equals 200,000, N equals 10,000. This is the high dimensional case. So the framework works without separating high dimension or not high dimensions.
Sounds clear. So there's another follow-up question. So there's an anonymous attendee asks, by having accuracy and false alarm rates, are we assuming the support for beta is discrete or not?
In this experiment we do, but the support to be able to have this type of figures, you have to know the ground truth. In the ground truth, we have beta, a particular beta. My recollection was 1 and minus 1, 1 minus 1 and 0. But the same phenomenon holds even if beta is the betas have continuous values.
Okay, great. Yeah, there are some follow-up questions. I will leave those in the end in order not to disrupt you here. Yeah, please continue. Yeah.
So this is our first story. My second story is in matrix completion. So what is matrix completion? Well-known problem. So you are given a matrix A for which only a set omega of Aij is known. The rest are not known. For example, in the Netflix competition of maybe 12, 13 years ago, you have on the horizon, the rows are, let's say, people, and the columns are movies. So, and then an element, Aij, if it is defined, it is a number between, let's say, 1 and 5 of the degree of attractiveness of that person to that movie. However, a person can only see maybe 100, 200, 300 movies, haven't seen 100,000 movies. So most of the Aijs are unknown, are question marks. So matrix completion asks for the following. You would like to find a matrix X, full matrix, Aij is a partial matrix, such that on whenever Aij is known, Xij minus Aij is small, but the rank of X is K, let's say K equals 10, meaning that only 10 factors are relevant for understanding, influencing how a person likes a movie. And that's, I think, this idea of having a reduced rank, some sparsity in the preferences without specifying what the factors are, is of interest. It has been utilized in many other areas in the last decade, motivated by the Netflix competition. Now, and people have developed methods for solving this problem using convex relaxations. But that's not what I'm going to do. I'm going to do also something further. I'm going to talk about interpretable matrix completion. So for every column J, we have some features that we call side information. For example, let's say a movie, columns are represented by movies. So a movie has, let's say, 10 characteristics. Its genre, its, let's say, its the receipts it have in theaters, the identity of the director, and so there are finite, many, small number of dimensional features that are a priori known for a particular movie, right? So we know the characteristics of a movie, okay? So we represent this, so for every movie and every factor by a matrix B. This is typically known. So that's why I call this a side data. So what we want, given potential side data, the rank condition can be rewritten as a sparsity condition over the P binary variables, namely, let's say you have 100 side data, from who the director is, who are the major actors, the genre of the movie, and so forth. But we say only K of them matter. So this number K is the same number as the rank. So in essence, what we are saying is not now I have this B matrix known, which for movies it is known. So what we want is to write X equals U, unknown, S a diagonal matrix whose elements are binary and they sum to K, times B, the side information. So B is known, S is not known but binary. This is what models the rank condition, and U is a factor matrix that says relative to this side data, each person has its own coefficients. So for example, for person 1, we have, let's say, 1, 5, and 7, 3 factors that matter. Person 1 has these coefficients in a linear setting. Person 2 has different coefficients, but the same variables. So this is what I call interpretable matrix completion. Interpretable because now, when we say the rank is K, it's very tough to understand. But if you say the rank is now K in the side information setting, you know which factors matter in people's making a priori preferences for movies. And the U represents the degree of attractiveness for factor J. So this is now the interpretable matrix completion, in which mathematically in this problem, we optimize over U and over S. I pause for questions.
So I'm a little bit confused here for the B. So essentially, you are assuming that so X, the composition, one part B is known. But how sensitive it is in practice? Say I change the information. Say for example, I can do not include the identity of the so say some information of the directors. And if we add that, how do you choose that in practice? Because there are many ways to choose.
Let's take the Netflix competition. The Netflix competition tells you the people and the specific movies.
Yeah.
Right? Specific movies. You go to publicly available data. Let's say the movie is Titanic. All right?
Yeah.
So you can generate data. If you look at Titanic in the websites or Rotten Tomatoes and so forth, you can find lots of side information about Titanic. You can find who the director is, if the movie had Oscars, what are the gross sales of the movie the previous year, cumulatively, the time it has been in theaters, the major actor. So this information is available. We don't use it in matrix completion, but to our peril. No, this is not correct. We should be using whatever information we have, we should be using it. So in this case, we know the movie, so we can find through public data what the matrix B is. So to say it's low rank it's one, of course, you might, that's more general. Now I'm making a particular assumption. I say, which I think is reasonable in real life, that people appreciate things on a sparsity pattern. For example, let's take how we make friends. Let's say there are, a person has many attributes. So the key thing I'm saying here is that people appreciate 10 attributes, 20 attributes, but not a million attributes. But in addition, B is known, which in many applications I have worked is known. For example, let's say you have people and drugs, right? So we know what the molecular structure of the drug is. So there are characteristics of this drug. So the B is typically known.
Okay.
You see what I mean?
Yes. And
so that's the motivation. It's not identical problems.
Yeah. No, I understand. Yeah.
But this is motivation where side information might be relevant, and I think we should use it.
Yes. So there are some questions from audience. Say, so the first is I can answer. So the rank of X is smaller or equal to K, but yeah. And the next question is how U is obtained. So the
U is a matrix N by P.
Yeah. Okay. I think
but this is unknown. This is unknown.
Yeah, U is unknown, right? Yeah.
So overall, therefore, the problem is as follows. I now regularized it. So U is unknown. But remember now, this is close to what I have presented before, because now I have the discrete elements, the continuous element, B is known. So the whole problem is to minimize over discrete, the minimum over U. X is U S B. It's very similar to what I have said before. You can solve this in closed form. You have to do it in matrix notation and so forth. So it's a bit more complicated, but not that complicated. So in the end of the day, the problem I indicated can be solved exactly by solving C of S, which now is the sum of the similar functions I had before, but very, very similar actually. So it's a convex optimization problem subject to binary variables. By using similar methods, we can solve the problem as before. And look at how it scales. So these are now real data from Netflix. We use K equals 5 for 5 factors. Similar results are for others. So this is our method. IMC is a method that uses the convex approximation. These are sort of state-of-the-art methods, not using the information, this only uses the rank. It doesn't use the side information. What you observe is from a time perspective, we can solve these problems reasonably fast, not, as the number increases, this is now 15,000 movies and roughly 500,000 people. We utilize 59 factors, choose 5. And what we observe is that the mean absolute error is actually better than alternatives. It makes sense. There are 2 reasons why the method is stronger. Number 1, it's more exact. Number 2, it uses auxiliary data. So what this suggests, and since then we have actually applied it to other problems in molecular biology and personalized medicine, and the sizes were much larger. M was in the 50,000, N was in the millions. And we have some of these methods did not were not able to solve the problems as they become much larger. This problem we were able to solve it. So this suggests that the idea of using side data in the context of discrete optimization using counting planes can have something to say also on matrix problems. I pause for questions.
One question is, how could we set a proper value scale of every feature in B to ensure that each row of B is proper? So I think what the audience means that all the features you collect might have some, say, for example, from different sources, and you need to rescale it, or there might be some missing values for some features for some movies.
Yes, the way, of course, we do it, we don't have missing values. We have B is a full matrix. So let's say, for example, we have 14,000 movies. One of the characteristics, let's say, is gross sales. We have this data. One of the others, who is the director? We have this data. Who is the primary actor? We will have this data. It's our selection what P is, how many factors we want to use. We select this based on the data we have. So it's not to our advantage to include a lot of missing data. So we select factors for which we have full. Of course, you can do imputations, but after a while, you might actually affect the story. So we have tried it for Netflix with real data. Given the availability of information on movies, that's not a big problem. We have also done it for biology and sequencing of tumors. All this data is available.
Sure.
I'm not saying there are no missing data, but we have a selection of what to use.
Yeah. Sure.
All right.
All right. Yeah.
Final topic. So we are all very used to randomization. For example, so what do we do if we are given some data? What do we teach our students? We say for a given data, we select a random subset, we place it on the side, that's the test set. On the remaining data, we randomly split into training and validation. We build models on training. Models have parameters. We perfect the parameters on the validation set. We perhaps iterate multiple times. In the end, we say these are the right parameters. Let's take Lasso, for example. We split it into validation, learning, validation and test, training, validation and test, but randomly, say 80%, 10%, and 10%. We pick lambda based on the 80, 10% validation. We find the best lambda. And then once we detect what the lambda is, we run a whole process on the 90% of the data. We find now the betas for that set of lambdas, and then we output the test, the betas that we found. We output how good the method is on the test set. I hope this suggests this is something that many people have tried. Same thing here. I have tried multiple. Let me illustrate this. So suppose you have 350 patients and you have 55 factors. And the 55 factors are 10 baseline variables, age, sex, cholesterol levels, etc., and their pairwise interactions. So you have 10 plus 10 choose 2. 10 choose 2 is 45. 45 plus 10 is 55. So that's the problem we have. And our objective is to predict hemoglobin, how much glucose we have a year later. So we use ordinary least squares on the original data. We randomly select different training sets. And these are the coefficients on the data. That's one run. That's another run. Something unusual happens. Look at the coefficients in one run and another run. The LDL coefficient, the HDL change signs. So in other words, that's not a good property of models. Models should not be affected by randomly selecting the sets. So you want some level of stability, namely that the betas do not change drastically if you change the selection of training in one iteration versus another. So with this motivation, I would like also to remind you, how do you guys train for exams? Well, I'll tell you how I train for exams. Let's say a qualifying exam, we take an exam and we observe in practice exam, and we observe two areas that I'm not so good at. Then I focus on these two areas. I become better at it. I don't randomly select tests. I basically focus on areas that I'm weaker at. Suppose, how do you train for marathons? You don't, for example, suppose you detect, I'm not a runner, but I spoke with others. Suppose you observe that people are not good in hilly roads, right? So they try to perfect this. They try to train not randomly. You don't take random streets to train on. Rather, you take areas that you are weaker. What is the corresponding thing in mathematics? rather than using randomization, let's try to use optimization. Namely, suppose you say, I have data 1 to n, and I have a variable zi, 0 or 1, whether I select this in the training set or not. So basically, I take randomly the test set and I put aside. So now I have, let's say, 100 observations that are going to be either training or validation. The test sets I set aside anyway, randomly. So among the two, I have a variable zi, 0 or 1, that I select 1, the point to be in the training set or not. So now the problem is I want to minimize beta, regular regression. I just use absolute value because I'm about to use linear optimization. Quadratic also works. The maximum over z. So I basically train among the worst set. Yeah. So I optimize over beta, the worst case over the choice. Let's say k equals 70. I find the 70, I find the beta outside that optimizes the sum of residuals, but the worst residuals, plus a regularization, could be the lasso or elastic net or ridge. I pose for questions on the logic of this idea.
So the logic, I actually have a question. So in the worst case, usually we can view the several worst cases as outliers. But in your approach, then you like weight those outliers very much. So should we? So
I don't weed them out. I want to, but what is an outlier? The choice of beta affects what is an outlier, right? Because the residual is affected by beta.
Yeah.
What I'm saying, I would like to find a regression that does well on the tougher set.
Yeah.
That's philosophically different.
Yeah.
Not randomly, but which why I gave you the example of how do you train for exams.
Yeah.
You train not by random questions. You train by the tougher questions. And since all of you are either professors or PhDs and so forth, you are all fantastic students in your past. I'm certain you can sympathize with what I'm saying. I don't believe, I definitely did not do this. I did not take random questions and I trained on them. I trained increasingly questions that I was weaker at, and then I improved.
Yeah, yeah.
So that's the logic.
Yes. So one question is, is Z also present in gamma? So I think it's no, right?
No, there's no Z here.
Yeah.
So this one I can put outside.
Yeah, and is there any particular reason that in the loss you use L1 loss instead?
No, there's no reason. It could be squares. Okay. It could be many others.
Okay, sure.
You will see why, how it is affecting. But in the paper with Ivan at JMLR, we use both.
Okay.
Quadratic loss and absolute value loss.
Yeah, and then we have some more questions.
Okay.
But to compute the max over Z, don't we need to mean over beta within to get the training error? So,
no, I want to find the minimum beta that optimizes the worst residuals. So the right sequence is minimum over beta, maximum over Z.
Yes. So next question is, why is it called stable? It does not capture the relative value difference.
You will see why I call it stable.
Yeah. And finally, a question by Rob. So does your min-max optimization problem have special or desirable statistical properties in theory?
In theory. So let me table this question first. I mean, I have, this is not something I worry about this type of analysis because, of course, if we make properties, if we random, we have to assume how data is generated. So once you assume how data is generated, one can potentially prove nice properties about unbiasedness and consistency and so forth. But the real world, data is not generated at random. Data is generated in the real world. So what I would like to see, what I set out to observe here and examine is the effectiveness on stability. And I will comment in a minute when we start doing experiments. So the evidence we gave in this case were experimental and empirical, not theoretical. I would like to motivate the audience to potentially prove interesting things. I'm certain it's feasible. We have not done it.
Yeah, and finally, a question that I'm also interested in your view. So you mostly mentioned that the penalization term, the gamma here, to be lasso, elastic net, or those convex penalties. So yes. What if we change them to non-convex penalties like the scat?
The approach would work.
Yeah. So in your view, how they differ from L0 penalty? I mean, so is it in the middle?
The L0 would work as well. In fact, we see experiment. So please view this as a, that's why I put it gamma. This could be the L0. The key here, the key idea is it applies for any type of regression you want.
Okay.
The key idea is the Z. That's the new idea. What we have here, it could be general. And in fact, in the experiments, I do also L0 regression.
Sure. Yeah, that's all questions we have. Yeah.
All right, thank you. Yeah. So let's do some analysis. So I'm now going, as function of Z, this function is linear in Z. So this set, maximizing a linear function over Z, is equivalent maximizing this over the extreme points of this set. Is the same, and the extreme point is the convex hull. So the convex hull is the sum of ZIs equals K, not anymore discrete, but continuous, because the extreme points of that set are binaries. So optimizing over this set or optimizing over Z is the same, right? But now, this is a linear programming problem. Maximizing Z over a continuous from a polyhedral is equivalent to a dual problem. The dual problem is minimizing over beta from before, theta and U. Theta is the dual variable, so the sum of Zi is equals K, the theta, and then Zi is less than K has also dual variables, so Ui. So the objective is to minimize, so this problem, the dual problem is minimize K theta plus the sum of Ui's, theta plus Ui's greater than the absolute value, Ui greater than or equal to 0. So this nonlinearity, it separates. So if you had quadratic here, there would be a quadratic. So instead of being a linear optimization problem, it would have been a quadratic constraint, but convex quadratic optimization problem. So in the end of the day, the whole problem we need to solve is to minimize beta, theta, and U to optimize these linear values. So now, if what value we have on beta when we have, let's say, if it's L1, if we have lasso, that's a linear programming problem. If we have ridge regression, is a quadratic. If we have non-linearity, non-convexity, it could be a non-convex problem. But still the same principle holds, okay? By using duality. It's easier to illustrate with for linear, but it can also work with quadratic as well. With me? I assume.
Yes, yes. Yeah.
So let's look at why I call it stable, all right? So these are various data sets, smaller on the smaller side, not tiny, but smaller. So this is the randomization approach where we randomize over maybe 50. So that's the average of the mean square error. So we use, let's say, 50-50 validation and training, 50-50 optimization. Smaller numbers are better, right? So you observe, let's say 70-30, by optimization is uniformly stronger as opposed to randomization, okay? That's not why I call it stable. This is the prediction standard deviation. So in this case, this is standard deviation of the for the prediction, because depending on if you have a random set, you have different predictions. So you observe that the standard deviation here is also more attractive, not every time, but often, right? overall better, the prediction of the standard deviation. And this is the standard deviation for the coefficients, which is why I call it more stable. So this is the stability. Remember the diabetes example where the coefficient changed drastically. So it's not a gigantic, for these sets, these are smaller sets, but by and large, not in every situation, the standard deviation of the coefficients of this type of regression was stronger, smaller than the randomization. And it makes some intuitive sense. Optimization selects which ones to go after, the worst case. It doesn't randomize. So it makes some sense if you repeat the experiments that things are better. Not every single time. I'm not claiming that, but overall. On support recovery, we can also do the L0 aspect, as you have asked me. And what we observe is if the support is known, the accuracy of the optimization method versus the randomization method, there's a delta. If we know the support, of course, in practice, we don't know the support. And the false recovery also is better. So optimization is better than randomization on also false recovery. If the support is unknown, so we use validation sets for the support recovery, and because it's unknown, the accuracy is still better. The red is above, but not by its huge amounts. So in other words, we have declined on and the false recovery also is stronger. In similar conclusions, known or unknown support. Given that my time is near completion, so hopefully you got a sense. So the similar results we have done for sparse classification, for tensor completion, for sparse inverse covariance estimation, factor analysis, sparse PCA. Many of these results, actually all of these results, are in the book I mentioned, Machine Learning Under a Modern Optimization Lens. And then other extensions of randomization versus optimization, optimal design of experiments, identifying exceptional responders, bootstrap, stable trees, and so forth, as opposed to using random forest. This idea of using randomization, optimization versus randomization is, in my opinion, not widely observed in statistics and statistical environments, because people think about randomization as something positive that can help things, but randomization also could perhaps be improved by using optimization ideas. That's the summary of my story today. I presented to you sparse regressions that is capable of solving problems with hundreds of thousands of observations and variables in minutes, that it has a significant edge in detecting sparsity and particularly in false detection, that there is an edge, in my view, of using optimization versus randomization. But very importantly, in my view, we have to reconsider deep-rooted beliefs on complexity and the need for relaxations that is clearly present in statistics departments around the world to solve sparse problems. I think mixed integer optimization problems are not as intractable as people believed. And this belief at the time, the opinion was formed, was correct. It was not very tractable, but things change with science. And as I mentioned, there's a new book, and I have now a new class for the last few years at MIT called Machine Learning Under a Modern Optimization Lens. And on that, I would like to conclude and thank you for being with me for the last 55 minutes. And I open it for questions and comments.
Yeah, thank you for the great talk. So let's see the questions we have. So one question is from Janet. So any intuition why for large problems, the dual problem will be faster to solve?
You mean the dual problem in the sparse regression or in the?
He or she didn't specify. So I think in the randomization part.
Yeah. This is a problem that solves in seconds for large scale. I mean, these are LPs nowadays. If you can solve problems of hundreds of thousands of variables, integer programs in minutes, you can solve similar problems in seconds. So this problem scales extraordinarily well.
Yes, yes.
Because it's an LP, it's not a or QP. I mean, this scales. This is not its problem. The problem is how well it works.
Yeah. So yeah, one comment from an audience, Yiming, says stable regression formulation seems to be related to a method proposed in machine learning conference called average top K method. So I personally don't know this paper. So the paper is called Learning with Average Top K Loss. That it was published at NeurIPS 2017. And that's
unfortunately, I do not know the paper, but if the person who asked the question can send me an email with this information, clearly I will take a look and I thank the audience for this, but I do not know the paper.
Right. Yeah, I also don't know the paper. So I just have one question for the last part, the randomization. So if we do several randomizations and we take the average, I mean, means that just like the idea of cross validation. In the first time, we use the first 80 samples. In the second time.
Yeah, I understand. Yeah, the cross validation is the paper. In fact, the reviewers of the paper have asked us to do it. We have done it. We have found that cross validation is better than validation set, but still our optimization method has an edge. Smaller edge, but it still has an edge.
Okay, great. Yeah, and that's all questions we here. And one more question. In the Sparse high-dimensional regression paper, how do you come with a new idea compared with your paper in 2016? I believe the paper by you with Rahul. So which use the big M and MIP ideas. So I personally think the new formulation removes the big M term, so it makes it much faster, right?
That's right. That's the key. So the reason I was looking for that is because I was unhappy. I do believe the paper with Rahul in 2016, it was an advance. It was an improved. It basically demonstrated, it put mixed integer in the map.
Okay.
But it still did not scale at these levels.
Yeah.
So I was always so I started experimenting, and we stumbled with this unusual idea that we formulate the problem not in the usual way, but in a nonlinear way. Basically, it required to change our view on formulations in ways that's not common. And in fact, with two of my students recently, we have extended this idea to general integer optimization with fantastic results. So namely, this idea of utilizing nonlinear formulations is an idea that helped us in solving problems that were not feasible to solve before. Network design, facility location. There's a paper that we have that you can find in archives. It's called, I forget the exact title, but has unified in the title, unified approach, discrete optimization. I'm certain you can find it on my website or in the archives.
Yeah. So yeah, I think that's all questions we have. So any audience will email you with follow-up questions. Like Yiming will email you about the paper he mentioned. Yeah.
Of course.
Yeah.
Thank you very much.
Thank you again for the great talk.
Of course, my pleasure. Bye-bye.
Bye.
Thank you.